All right. Lockhart-Gilroy.
Hey, Mr. Lockhart-Gilroy.
All right, hi guys.
So confused.
How are you today?
I'm fine.
I'm fine too.
Okay. So, okay. All right. Hopefully, you're about to see my iPad come up.
It says you're screen sharing, so.
Got it?
Yep.
Excellent.
Nice.
Now, let's see if we can get these guys up.
Yes.
All right. I'm going to bring over a file, but we're going to do things a little differently than I planned because we're on the distance learning thing. So what we would have been doing is we would have been going through pair deck exercise, but I think we're just going to talk it through, and I'll show you what's going on. Also, I'm going to defer any questions you have from homework until we're back in school, because just again for the interest of time. Okay, we've got a little bit of lag, not too much, a little bit of lag. But hopefully you should be seeing a thing that says polar equations. If you're not seeing that, this is a good time to unmute yourself and chime in. Excellent. Take silence for assent. So far, right, what we've done in this chapter has not been very deep. We've learned how to plot points. And I know that sounds very silly, but without plotting points, then it's really sort of impossible to do anything more interesting. So as a quick reminder, we said that you can plot a polar point by saying, if you pick, 4, 30 degrees, it means go out to the 30-degree line and go out 4 units. And if you did, 5 or -5, 300, it meant go to the 300 line, but go 5 units the other way. So 300 is 30 over, so 30 over here. So we're talking about that point. And that's going to be everything we go on here, because now what we want to do is start plotting r as some function of theta. So if you remember back in Cartesian coordinates, we plotted the graph of something, and we said the graph was the collection of all ordered pairs x, f of x, where we said the y value of our coordinate was the function evaluated at the x value of our coordinate. And then we're going to do the same idea, but we're going to say that r is some function of theta. And so, make sure this is recording. Give me 1 second. I actually have this fear that it's not recording because this morning did something weird, and I want to make sure I have this available. So, okay. All right, well, it looks like it's recording. Guess we'll find out. And then we're going to plot r, theta. So we're going to say the function at theta at the angle we pick. We do this primarily because we can generally restrict the angle from 0 to 360, although that isn't always true and isn't really necessary. It's sort of traditional. Also, do notice that we flipped the order of the coordinates, and that's just unfortunate from way back when people invented this stuff, and they weren't thinking about it. All right, so we could plot a function like r is sine theta by finding just the values at various values of theta. The same way that you did a t-table way back in Algebra 0. They said you can plot a graph just by picking x's and figuring out the corresponding y. You can plot a graph here by picking theta and getting the corresponding r. And what we would have done together is sort of done this in class, but instead I'm just going to sort of jump to the answer. So we pick up all of these values of r at the corresponding angle of theta, and if we plot them sort of quickly, we might say, well, 0, 0 is that. That's pretty easy. 30.5 would be here. 45 and 0.71 would be something like that. 60 and 0.87 would be something like that. And then 90 gives us 1. And then we're at 120 and 0.87, and then at 1 35 and 7, 1, and then at a half for 150 again. So down to here. All right, so we're already getting something. We could imagine if we had picked more values of, more values, maybe we would have had it loop through. I'm looking for a decent color. Not a decent color. So, and it might do something like this. I'm kind of making some of that up, but we can see there's kind of a sketch here. Then it gets kind of interesting, though, because when we get to the green bits and we say at 180, we have 0 again, no big deal. But at 210, we have minus a half. So I go out the 210 line, but I have to go minus a half, so I end up over there. And then at 225, but minus 0.71, and then minus 0.8. And we see that one of the weird features that happens in this kind of graph is that it kind of duplicates. So actually, we only had to go up to 180 to get the entire graph. Sometimes that's obvious, sometimes it's not. It's sort of important to sort of look out there. But the final thing that comes out looks something like that. And if we did all of them, we'd find that it was just a circle, which is kind of uninteresting after all that work. But what we're going to do now, and I'm going to really go quickly through, but don't feel like you're supposed to read these. We were going to break into groups and do 4 different equations. This 3 minus 5 cos, this 3 sine 2 theta, 2 plus 2 sine theta, and 2 theta times the conversion factor. Because the guys will cut us off in about, well, probably a little under 35 minutes now, I don't want to spend that time. It's about 10 or 15 minutes. I regret that you won't have the joy of graphing things on your own, but I've sort of rigged a thing, and I want to sort of demonstrate with that. So hopefully, nothing like that, sorry. So I've rigged a Desmos file to do something similar for us, and what it's going to do is plot, in this case, it's going to plot 3 sine 2 theta, the way it's rigged right now. And it's going to do a little, I don't know if you can see the little green line on the x-axis. It's going to be like a radar sweep. In fact, let me show you that first. All right, so it's just going around, and it's just figuring out where that curve would be for each of these guys. All right, so I don't know, a little bit of radar-ish thing going off here. But what we really want with that, which I'll turn on when it comes around, is we'll start drawing the curve as it comes out. We can see where it is. All right, so this is now hitting many, many, many more values, theoretically, nominally all the values. And we can see that when we're in the 4th quadrant, we actually get 2nd quadrant answers because of the negative radius. Okay. So we'll let that go around again for a bit. This thing that came out, really fast, is called a rose, which is a little allegorical and fun and poetic because, hey, it was the 1600s. This is called a 4-petal rose because there are 4 of those little loops. I can change the number of petals by changing the number in front of theta. So to go back to this just for a second, this is our 4-petal rose, and we have this was what's controlling the number of petals. We'll do that in a second. This is just controlling how large it is. Notice that the largest value it gets to is 3. And that controls that. But it's kind of interesting to see what happens as we play around. So we say, and this Desmos file is linked online, so at some point you can play with it if you find it useful. If we pick, for instance, 4, we get more petals. In fact, we get 8 petals. If we pick 6, we get even more. We can see that the number in front of the angle gives us how many petals we get because we're basically cycling through really fast. That when we're at 1/8 of an angle, right, with only 1/8 of the way through the 1st quadrant, we've already looped around, and 8 times that's already more than 360, so we've looped around some. We get this cute little spirograph pattern going on. And if we look at it quickly, let's pause it here. Again, this, for instance, generated, what are we at, 8, right? So we'll have 16 petals. I wish I could draw on this, but. So we can see 1, 2, 3, 4, 5, 6, 7, 8, and twice as many. 6. So we have 16 petals. It gets kind of weird, though, when we go back down to a low number and we pick 3. And here we only get 3 petals, or 5 petals, or 7 petals. So there's a restriction sort of, which is weird, but if we have sine n theta, even n gives us twice as many petals, but odd n only gives us that many petals. If we had decided to do cosine instead of sine, which is perfectly acceptable, we see, not surprisingly, the same shape, but now it's been shifted by 90 degrees because cosine leads sine by 90 degrees. So it's been rotated. The figure gets rotated. Actually, it gets rotated by 90 over n, which is kind of interesting. All right, as we keep doing this, well, that's fine. And then you can do some weird stuff, which Desmos lets you do that people never would have done before computers. For instance, we can let n itself vary. So let's take n from 0 to 10. And we get something like that. Where every time n becomes an integer, we spawn off like a new leaf. And then the leaves get kind of weird and move on. So that's just kind of fun. There's not a lot of practical use for that. It's just kind of fun. It's also fun when you see what happens when n's less than 1, which will happen in a second. Right, this will go up. And you get this weird other thing going on as it's trying to figure out what it is, and then it will come down to be 1, 2, and so on. All right. We can have other shapes. So let's add somebody and that guy. Turn that guy off and put this as. So for instance, we might have R is some number. No, sure. Plus that same number times sine. I'm going to make the A a little smaller just to put it all on here. So we get this bean-shaped thing, which is technically usually called a cardioid. I guess it usually has a minus sign here. And it's supposed to look a little bit like a heart. I'm going to put the plus back so we can see it. Again, you can shift it by, rotate it by 90 degrees by making it a cosine. In this case, if we change A, all we do is change the scale. And the key thing that makes it a cardioid is that little divot at the bottom. So it's a cardioid because of this bit, that little pinch in there. Theoretically, people say it looks like a heart. It doesn't really look like a heart to me, but I guess that's why we call it that. If instead we say that we have two different numbers, put that guy in, then we have what's called a limison, especially when b gets large. So in this case, when we have a is less than b, then we get this weird little loop in the middle there. And that's what's called limison. Go back and show you that word. All right. Sorry, this is a cosine, but this little divot here, this little loop here, is what makes it a limison, and it's because the two constants are unequal. So we get those two. And in fact, that a is less than b. This happened to be a cosine guy. You can see then that the sort of cardioid ends up being the limiting case of that. If I sort of bring these guys down. Play with B. When B comes down, you see that when it's 2, it's going to pinch off and become the cardioid. And then it becomes just this kind of flattened, weird.
Wait, what happens when, like, it's A minus B sine of theta? Oh.
Okay, so A minus B sine theta flips it to the other way. The minus sign is, again, a rotation of 180. So it just works, it's as if it were flipped around, actually spun around the axis.
Okay.
It's a little unbearing. But it's sort of important to understand that the cardioid is a special case. It is, I mean, it's an important special case because that difference is 0. And then it flattens down and becomes that weird, like, bumpy apple type thing, which no one ever talks about when the size of A is less than the size of B. All right. And then I think there's really sort of two others that we worried about. So let's hide the cardioid, etc. There is a case where you have a square, which I can't plot directly, so I'm going to plot as a square root on both sides. And we're going to say if it's some number times sine of the angle. Oops. Sorry, it's unhappy because I didn't put an equal sign. And then we're going to make it a, we're going to give it a partner because it's really r squared equals something. So I'm going to put plus and minus of the same thing. And let's try and make them the same color. And then we get this thing called a lemniscate, which is a weird and hard word to pronounce. And it basically looks, lemniscates are things that look like infinity signs or eights, things that cross themselves in the middle. We will not deal with higher multiples than 1, although it's Desmos, so we could totally say, hey, Desmos, what if we put a 2 in here? And then you get this weird, right, looks a little bit more like an infinity sign. But we're not gonna, I'm not going to ask you to be responsible for picking out what the power or the factor of n is on that. But I would like you to be able to factor out what the value of a is, for instance. But it's not that hard. This guy is kind of goofy because I didn't pick a good one, so I'm going to make it a little easier to see. But again, we can say, well, the maximum value that our curve gets is 2, and the maximum value that our equation gets, sine can only be at most 1, so we have square root of a. So square root of a must be 2, or a is 4. That's all that's saying. I guess everything else is just a scale factor. It doesn't do anything fun and interesting. All right. And then the last one that I wanted to sort of tell you about is an entirely different beast. So let's turn off this guy. And that one is r is just some multiple of theta. And I'm going to make a relatively small. Well, let's make it a1, just make that easy. All right, what comes out in that case is something called the spiral of Archimedes. And this shows up a lot in nature. A couple of important limitations for Desmos. Desmos only goes around some number of times. It doesn't go, obviously, from 0 to infinity. So at some point, it just gives up. It must do what looks to be 1, 2, 3, 4, 5, 6. It looks like 7 pi is their largest value of theta. And there's probably somewhere in Desmos that we can tell it to use more or less, but that's not particularly interesting. What I like about the spiral and why I wanted to flag it for you is coterminal angles are not the same for a thing that's undergoing, that has the spiral. So we're used to thinking that, oh, well, 360 is the same as 0, or 720 is the same as 360, or 450 is the same as 90. But that's always been kind of a conceit, because what's really going on here is that cosine and sine have a period of 360 degrees, so anything that involves cosine or sine will repeat every 360. But the Archimedean spiral doesn't have a trig function in it, so it doesn't repeat that way. It doesn't have any issue where it says, oh, it's the same number at 360 or wherever we are. So if we watch this guy play out, which is kind of fun, if we watch this guy play out, oops, I guess it's not, sorry, the radar speaker isn't really set up to do that correctly. I should be doing, oh, actually, no, it doesn't work at all. I was going to try and make the radar sweep work, but it won't. Turn that off. It really wasn't rigged for this guy. But as we go around, we can sort of see what happens as we go around at least. That it goes, it tries to follow this around, but 320 is not the same. 2 pi is not the same as 0 because we're just multiplying by it. So it's just important to remind people that there's no magic to those coterminal things. It's only in certain cases, although those cases are really important. So what we would have done in class is we would have walked through these together. But what I really want you to know about is sort of this thing at the end of the notes. And I'm still going to upload the notes because the exercise isn't that useful, but this little thing here is actually particularly useful. is this little like taxonomy, this little zoology of the different classical curves. To be fair, there's no reason why these are around other than historical. Like, there's no reason that you can put other things out there. These sort of win by being the easiest ones to graph before there were computers, right? In today's world, I really should have you just go wild on Desmos and play around with stuff and discover your own special curves. But these are the ones that are sort of generally studied. That are generally studied because they're semi-historical and they're sort of useful. The n-petaled rows and the spiral Archimedes are the ones that are probably most particularly useful. Cardioids show up a bit in radio transmission, believe it or not. That you have a directional antenna, the intensity tends to follow some sort of cardioid. I can't tell you, I have no idea when a limison shows up or not. So in a more pragmatic viewpoint, if you're a student who's like, but what do I have to know? You do actually have to be able to identify them, and the way that the homework that's online tonight, and it isn't from the textbook, so you'll have to download it, is basically to throw these guys. I basically give you graphs. I guess we can look at one of those. So I give you some graphs, and I ask you to come up with the equations that fit them. So we'll take a look at one of those, and then I think we'll be done, even though it's a little bit earlier than technically we're supposed to be. That's okay. Not that much earlier. But so reproduce that thing for you here, so you have it in place. And the basic idea is just classify the graph and write an equation that produces it. So we look at this and we say, oh, it's got the little pinched end but no loop, so it's a cardioid. And then we say cardioids have maximum values that are 2a, because the cardioid is a plus, in this case, well, I guess in this case because it's below the axis. Let's go through the whole thing. It's a cardioid, so its sort of root form is a plus a sine theta. That's in the taxonomy here. But we see that that cardioid is directly up and our cardioid is directly down. So really it's going to be a minus a sine theta. And that's what flips it around the axis, or rotates around the axis. And then we say, well, when is this, what's the maximum value of this? Well, that would be when sine is minus 1, or 2a. And the maximum value we have is 6. So we have 6 equals 2a, or a is 3. So the actual output would be, this equation would be 3 minus 3 sine theta. There's a way of cheating, and I don't care that much that you do it at this point, but I'm not sure we're going to be able to get Desmos working for you for your test, so I think you want to know how to do this by hand. You could go into Desmos, type in the root formula, and just play with values of a until they synced up, that you pick some point that's easy to evaluate, that's not trivial, like the center. And you say, like here, at 3 pi over 2, at 3 pi over 2, its R value is 6, and you just play that in. You just make sure the graph fits that graph. So if we go, okay.
Wait, I'm just a little confused about where you got sine of -1 for the previous one.
Okay, so for this guy, which I'm going to show you on Desmos, but I'm saying that when will this R be maximized? All right, that's what I'm asking. Because I can read from the graph that it's maximized with a value of 6. If I look at my equation, this whole thing will be maximal when this is minus 1. Because sine is trapped between minus 1 and 1. And this flips the sine of us. So when sine is minus 1, then this whole thing is as large as it can get. I don't care what the angle is that makes it minus 1, to be honest. All I care about is when sine of the angle is minus 1, then a becomes a minus, the R becomes a minus a times minus 1, or R equals a plus a, which is 2a.
Okay, all right.
All right?
Yeah, that makes sense.
But if you don't like playing around with that, you can certainly go here to Desmos, and you can say, well, I know that it has to be of the form R is something, and I'm going to cheat a little bit because we know it should be minus that thing times sine. And I say, let's add that. And then I can just play and say, well, mine went to 6, so let me just drag the slider until such time as it looks like my curve. So I pick that. Oops. So hard to do by hand. There we go. And I say that that looks like my guy. The wrong color, but it goes through the correct points. Right? It crosses through at 270, it's 6. At 0, it's 3, etc. So it must be whatever value of A came out, which was 3. So that's sort of a quick and dirty way to do it without doing a lot of analysis. But even if you had to do the analysis, it really means pick some point whose angle and distance you know and force your equation to go through that point. Mr. Gupta, if it makes you feel, I don't want to say feel better, if you want to think of a different way of thinking about it, you can say, well, I have R is A minus A sine theta. And over here, when theta equals 3 pi over 2, R is 6, which I'm just reading from the graph. I'm just picking some point on the graph, which is easy to read. And so I can just say that 6 is A minus A sine 3 pi over 2. Just force it to fit that equation. Sine of 3 pi over 2 is minus 1. So then we're back to what I had before. A minus A, this whole thing was minus 1. So it's A plus A, where 6 equals 2A. And again, A equals 3. So that's sort of 3, certainly not distinct, but different ways of getting the same thing out. All of them come down to basically picking some easy point on your graph and doing it. So a few of these are worked out. I think I actually have a few of them worked out online, to be honest. But I think if you look at the homework, there's some there. But I asked you to do, I think, 5 of them or something like that. Let's see. So 6 of them, I suppose. All right, and then the idea is that when you see this in a testing environment, I can promise you that on your next test, the way that I will ask you about polar graphs is literally a question like this. Here is a polar graph, write the equation that would produce it. All right, well, Zoom is telling me I'm about to be thrown off anyway. I think we're probably 8 minutes shy of the way the class is supposed to go. So if you have any questions on either section 1 or section 2, we'll tackle those at the start of the next class, which I guess for us should be tomorrow if there's not more sudden surprise snow. All right, folks, have a good day.
Thank you.
Kai out.